All right, so thanks a lot. Yeah, thanks to the organizers for setting this up. Thanks to all of us for being here. My name is Jean-Christophe Mourrat, or JC Mourrat. You will find my email in the list of participants and also on the web. If you want to contact me, please feel free to do so. I thought that because maybe some of you do not have a ton of experience with summer schools or conferences, I would like to share my personal thoughts about this first. In my own personal experience, a lot of the interesting things that happen during conferences or summer schools happens outside of the talks. And so I would like to encourage you to not be shy during these 2 weeks and go and talk with other people. I would like to remind you also that the organizers have sent you the list of participants on top of the list of talks that we have in the booklet. So, if you see that you would like to talk to someone, you don't need to wait until you bump into them by chance or you see their talk or whatever. You can send them an email and say, hey, I would like to talk to you. I think it would be nice. Yeah, in my opinion, there's a lot of value to doing this. And similarly, I encourage you a lot to talk to me if you think that that could be an interesting conversation to have. That can be on the things I'm going to lecture about. That can be also on things I've done in the past. Maybe I remember them a bit less well, but I'll try my best. So yeah, I encourage you to go and talk to me. But I also try to experiment with some online way for you to give me feedback on the lectures. And the email address for doing this is like this. What did I say? So tinyurl.com/sf like Saint-Flour, JC like me, and then Paul. Is that right? Yes. So if you go to there, you will find a form where you can say a bunch of things like if you think I'm going too slow, if you think I'm going too fast, if you think I'm doing okay. If you think that there are things that are confusing in the lecture, you can say. Anyway, like you can give me feedback, and you can give it every day for the lecture you just seen. Okay? All right, so are there questions on the organization of the lectures? That's good. Okay. So yeah, please, I will not perhaps remember to remind you each time, but please feel free to interrupt me when I lecture. I really appreciate that we interact with each other. It's not just me speaking alone. All right, so I think we're ready to start the lecture now. So the goal of the lectures I'm going to give you is going to discuss mean-field systems with disordered interactions. By this I mean systems that are made of a very large number of elementary things, elementary units. And each of these units on its own is going to want to have direct interactions with other units in a rather simple way, but a simple way that will incorporate some disorder. Maybe some will want to cooperate with each other, and some will want to kind of anti-cooperate, like to be kind of in disagreement with the other unit. And the goal of the questions we're going to ask ourselves is what's happening globally for the system on its own, on the whole, because of these interactions. When the system becomes very large, we're going to try to see if we can do things mathematically to understand what's going on. So I want to focus in particular on two particular classes of models that have these sort of features. One of the two things which perhaps most directly embodies this sort of description I gave informally is called spin glasses. I'm going to give you an example of a spin glass in a minute. And the other class of models I want to discuss is coming from statistical inference in high dimension. So it's going to be a problem of the form, there are many, many variables that we want to infer, and we observe them in some way that also has some disorder in the way we observe it. And we're going to try to understand how much of these variables we can recover from our observation. And for some reason, which right now is not very obvious, these systems are related to those I described earlier. And a third class of models that we are also going to discuss is going to be kind of similar sort of models, but that do not have the disorder part. It's just units that maybe all want to cooperate with each other. So they don't fit with the actual title I gave, statistical mechanics of disordered systems, but we'll still spend a significant amount of time studying them because they are simpler. And because they are simpler, we can train our techniques to see how we can understand these things, etc. So for these systems, there are many, many ways to solve them, but we're going to try to develop techniques that are as robust as we can, and so hopefully they will extend well to more difficult classes. And along the way, I'm going to be rather single-minded in the sort of question I want to ask about these systems. I'm going to focus on trying to calculate a quantity that often is called the free energy of these systems. You can think of it as a sort of Laplace transform of the quantities that we would like to understand. The reason I want to focus on this is that experience has suggested time and again that this is really the first thing you should do. It's kind of maybe the most approachable thing that really gives you good insight into these systems. Okay, so I want to focus on this. And physicists have also their own understanding of why this quantity really makes sense. So I really want to kind of focus on this specific question, on these three classes of models, the non-disordered, the statistical inference, and the spin glasses. And in order to do this, I'm going to try to emphasize a specific technique which is based on partial differential equations, specifically on Hamilton-Jacobi equations. This is my best attempt to understand these questions, but I don't claim this is the only possible route for trying to understand them. It's the one I'm going to present for reasons I'm going to try to convince you about. This is a probability summer school, so I want to clarify right away that I do not assume that you know in advance anything about partial differential equations. Okay? So hopefully I will try to walk you through how these PDEs work and the definition, why they make sense, etc., the kind of phenomenology, etc. What do I want to say? Yes, and perhaps one last word about the philosophy of the lectures is that my goal, let's say, is to try to build a very powerful toolbox for studying things, but most of the time I'm going to try to study the perhaps simplest possible base model where it makes sense, where the technique is doing something. And you'll just have to believe me that the tools really kind of transport well to more difficult cases. I claim that this is true, but maybe it will not always shine during the lectures because I want to kind of focus on simple things as much as I can. Yeah, and also one last comment about the, let's say, philosophy of what I thought about when I prepared the class. Maybe spin glasses are not your main interest, and it's not the thing you deeply want to focus on. Sorry. And so, but in any case, I try to, when I think that there is a topic that merits further study, even if you don't perhaps care about spin glasses, then I'm willing to spend a decent amount of time explaining this part, even though it's perhaps not the most direct route. So for instance, I don't know, understanding these Hamilton-Jacobi equations, I think is interesting in many different endeavors of mathematics. So, I think if you understand bits of the phenomenology of these things, it's not lost, even though maybe spin glasses will not be what you do next. All right, so that's it for the general comments. Now I'm going to slowly start, if that's fine. I mean, today I'm just going to try to give you a broad picture of what we're going to try to do. So it's going to be, the feeling will be a bit different from the other lectures. I'm going to be a bit vague and just try to give you a landscape sort of perspective. Okay? Makes sense. So this was very general chit-chat. Now I'm going to try to give you a more concrete example of what a spin glass is. I think the simplest possible example of a spin glass So let's say spin glass is a model called the Sherrington-Kirkpatrick model. So it was introduced by these two physicists, Sherrington and Kirkpatrick, I think sometime in the 70s. I'm going to call it the SK model from now on. And it's defined like this. So, well, okay, maybe I'm going to give you a little story about motivating the model, which is not the one that these guys had in mind, but that's fine. So imagine that you have a bunch of individuals and you want to, okay, so let me write this. So there are individuals like us in this room. And perhaps I'm just going to index them by the integers instead of giving them first names because it's kind of simpler. And so we have these individuals, and I also have another piece of information about these individuals. It's the way they interact with each other. You know, I know for each pair of individuals if they like each other or not. So coefficients, let's say. Wij. The quality, let's say. Of the interaction between I and J. By the way, can everybody read me okay? Even at the back? Fine.
Real numbers.
Yeah, they are real numbers. Yeah, thanks for the question. These are real numbers, and in particular, they can be positive or negative. So if they are positive and large, we understand that I likes J very much. And if it's negative and large, we understand that I really dislikes J a lot. Okay, and once we have this, our task is to try to find a partition of the set of individuals into two groups so that as much as we can, people are happy in their group and the people they don't like are in the other group, okay? So the task is to split this into two groups. These individuals. Okay, I'm not going to write it, but it's to maximize happiness overall, okay? And one way to encode the assignment of these individuals into the two groups is to represent this by a vector, which I'm going to denote by sigma, a vector of +1 and -1. Okay, this is my shorthand for the set +1, -1. And I understand that if sigma I is +1, individual I is put into group +1, and if sigma I is -1, it means individual I is put into the group -1, okay? So we want to maximize happiness, so maybe what I should write is that we are trying to maximize this function, sum over all I and j of wij, the indicator function that sigma I is equal to sigma j, meaning that individuals I and j are in the same group. Okay? Now, I'm going to change slightly the problem because so that it matches better the way it was introduced by Sherrington and Kirkpatrick, and also there are other motivations which perhaps will become clearer later. But it's going to stay relatively faithful to this question. So instead of this, I'm going to focus on this question. Trying to maximize this function, okay? Instead of writing the indicator function, I'm going to write the product sigma I, sigma j. Okay, so this is +1 if they are in the same group. This is -1 if they are not in the same group. Overall, there is some advantage to writing a polynomial in sigma, so I prefer this. And also, okay, for reasons, historical reasons I'm not going to explain, people actually wrote this down because they didn't think about individuals and splitting into two groups at the beginning. Okay. Okay, so this is the function I want to focus on. We want to understand how to maximize this function. And yeah, thanks to the clarification that I was asked, I did mention that this can be positive or negative. And so if you think about it for a minute, you'll see that this is going to be a difficult problem in general. It's not going to be easy to identify the best configuration that maximizes this function. And just to make this very clear, I'm going to illustrate this even on just 3 sites. So let's say we have these individuals I, J, and K. And let's imagine that the interaction, yes, so sometimes, okay, I'm being a little bit imprecise. Sometimes I think of interaction between I and J as being symmetric and sometimes not, but in general, it's slightly more convenient for me to assume that these are not symmetric coefficients. But you can see that you can just group them together. It's just some, let's say, I don't know, convention or something. So I'm kind of going back and forth a little bit when I speak between symmetry and no symmetry. But okay, let's just ignore this a little bit. So suppose that the interaction between I and J is positive. So they like each other. They want to be in the same group. So you want to put these 2 guys into the same group. And maybe the interaction between J and K is also positive. So you would also like to put J and K in the same group. But maybe it so happens that I and K don't like each other. And then you would rather like that I and K are not in the same group. And you see that even on 3 sites, on this very simple example, there is no way for you to make sure that every single pair is maximally satisfied. Okay? You will have to make a compromise. You will have to look at the exact value of the coefficients and try to make sure you find the correct configuration. Okay? So physicists in this case say that there is frustrations in the system, maybe because some pairs are not in their maximally preferred state. And when there are frustrations in systems like this, it's kind of synonymous with the fact that the material is glassy, or the system is glassy. It's like a glass. Okay, and perhaps I can make a small parenthesis that this is a word that they chose because they really thought it was analogous to what happens in the glass of the windows. So maybe I can explain this shortly. So in the windows, they don't expect to find coefficients that are kind of, anyway, they don't exactly think in these terms, but they think that, maybe I should first say some words about how glass is made in the first place. So if you want to make a glass, basically you take a bunch of sand and a couple of small other ingredients, of other ingredients in smaller quantities, and you heat it up, and then it melts, it becomes a liquid. And the key aspect to making the glass is that you have to cool this liquid very fast. Okay? If you slowly cool it down, then it will want to be in its crystal state, and this will not be a glass. If you want it to be a glass, you have to really freeze it very rapidly so that it's kind of trapped in this disordered kind of configuration that is the standard situation for liquids. And then it's trapped in this bizarre geometric configuration. And its preferred state is the crystal state. So it's going to still try to slowly evolve, but things are difficult, and maybe the geometry of this arrangement of atoms is bizarre. And so a bit like here, where finding the optimal configuration is kind of difficult. You have to make compromise, and finding the best possible configuration is difficult. Then perhaps the same sort of phenomenology occurs with the glass, where it's trying to reach its crystal state, but it's forever, trying to, I don't know exactly how to describe it, but I hope you see a little bit what I'm trying to picture. Is like maybe it would like to reach a better configuration, but in order to do this transformation, it needs first to do moves that are a priori not good for it. It has to first start to move in directions that are antagonistic to what is best for its energy, so that it can find the better configurations. So if you think in terms of energy landscapes, maybe you have to imagine that it's very rugged, and the best places are very difficult to find. You have to go through many little hills, maybe a bit like the landscapes here with many little hills if you want to go to a direction. Okay, so this is why it's called like this, a glass. And yeah, also for reasons I have not explained very much, oftentimes these variables are called spins. Okay, so this is why we are going to call this a spin glass. Okay, it's a bunch of spins and it's glassy, so why not a spin glass? Are there questions so far? It's good. Yes.
So what happens before we cool down the liquid slowly?
I think it will reach the crystal state, and then the aspect of it will be different, and so you will have failed to produce a glass. Are there?
It won't be transparent.
It won't be transparent. Yeah, I think. Yeah.
Quartz.
Yeah, exactly. And I think for physicists, really the signature of the glassy aspect also is that if you test aspects of the material, it will never equilibrate. Like it will evolve over time scales that are arbitrarily large. So for instance, if you test, I don't know how much your glass is bending or something, this will evolve over time scales. Starting from the moment when you prepare it, it will have some sort of change of behavior over. I don't know, if you do an experiment after 1 second, 2 seconds, 4 seconds, etc., you will see an evolution in this mechanical property. But if you do a similar experiment over the scale of 1 hour, 2 hours, 4 hours, etc., you will still see that things are evolving. And if you do like 1 day, 2 days, 4 days, etc., you will still see things evolving. If you do 1 year, 2 years, 4 years, you will still see things evolving. And to as long as people have managed to do the experiment, you will still see things evolving. It's never really reaching equilibrium. So I think when I present it, I stress this frustration part, but I think for physicists, it's really this dynamical kind of never reaching the equilibrium that is really the main signature of the phenomenology. Okay, well, if you cool it slowly, then it will just reach its equilibrium, and you're done. That's it. Okay. All right, so far I have not specified anything about these coefficients. And if you think about this problem in general, it's also interesting. It's totally fine, but what you can show in particular, for instance, I'm just mentioning, but I'm not going to discuss this further, is that this problem of I give you the coefficients, I ask you to find the configuration that maximizes this function is NP hard. Okay, so I'm not even going to say what that means, but even if you want to do it approximately, if you want to find a configuration that is approximately reaching the maximum of this function, even if you mean by approximately, you mean like gives you, I don't know, 1% of the value of the true maximum, which is really like a bad notion of approximate. This is still NP hard. Anyway, this is very interesting, but this is really focusing on the worst case sort of, very difficult W's. And this is not what I'm going to want to focus on. Instead, during these lectures, we're going to try to focus on maybe what you could describe as typical instances of this problem. And to be more specific, I'm going to assume that these coefficients are just picked at random at the beginning. Okay? So we assume these Wij's are independent and I'm going to just take them standard Gaussians just for definiteness. By standard, I mean they have mean 0 and variance 1. So really the key assumption here is not the Gaussian part, is that they are independent and identically distributed. Or at least, let's say, independent and with the same variance, that would still be fine. The key part is really independent and roughly the same order of magnitude. Okay, and so maybe this is really what qualifies as a spin glass model for real, is that you also add the way you also describe the way you pick the coefficients, and this you pick them at random. Okay. So that's it. This is the function I want to understand. For a random realization of the Wij's, can I understand aspects of this function here? Okay. Okay, jumping. Eraser. Not sure if I'm having a lot of success with erasing. Let's see if I do this, maybe it's better. Maybe that's better. Okay, so let me erase this as well. I realize I don't have time. All right, so I told you about, so I want to understand aspects of this function. And at the beginning, I told you about this thing called this free energy, this sort of Laplace transform of this object. So I'm going to introduce it now. So there's this. And let me write this. Maybe I'm going to write this in the... I'm going to give a name to this function I wrote there before I erase it. And I'm going to keep it there. So Hn of sigma, and I put this 1/square of n for reasons I'm going to explain in a second. Okay, so this is the function I want to understand. And well, depending on your, maybe I should try to, okay. Well. Depending on your background, maybe if you, we've polled people, and I've seen that many of you have already seen what a Gibbs measure is. So perhaps one question you could ask also in relation with this function is what is the behavior of the Gibbs measure that is associated with it for each parameter beta? And this means that you're going to build a probability measure on the space of configurations, the space of this +1, -1 to the power of n, that to each configuration sigma associates a probability proportional to this exponential. Okay? So maybe we also want to understand this. And a good way to approach the study of this Gibbs measure, or this probability measure, is to first try to understand the following quantity, which is what happens when you sum over all configurations, and you look at this. So this is what I'm calling a sort of Laplace transform of the quantity of interest. And this is a good time for me to explain why I've put a 1/square of n in the definition of Hn of sigma, is that this is what makes this quantity interesting as you vary beta. The reason is that if you set it up like this, maybe I'm not going to explain it, but in the lecture notes you'll find some exercise with solution where we explain that, for instance, the maximum of this function, if you put this normalization, will be over the n. And also, you will have several configurations that have this quantity be over the n. So you will have this guy be over the n, and you have this exponential. Okay, so some of these terms at least will be of the order exponential of n, and then you're also summing over a number of terms which is exponential in n. Okay, so this is the right way to balance this sort of, there are many configurations sort of aspect, the entropy aspect, and what's happening inside the exponential, the energy aspect. Okay, so as you slide the beta, you're going to interpolate between a situation where basically you don't really care what's the value of this guy, and it's just because there are many configurations that this is what's going on. And a situation when beta is large, where basically everything is carried by the few places where this is maximal. Okay, so this is really, and then as you slide beta, you can try to understand the transition between small beta, which will be easier to understand, kind of uniform over all configurations, and large beta, which is very related to the behavior of the maximum of this function. Okay, so I said this quantity will be roughly exponential in n. So in order to keep it under control, I'm going to take the log and divide by n. Okay, and this is a quantity that we can study, and this is what I'm going to call the free energy. Okay, so this is still a random quantity. Remember that we picked the coefficients wij at random. But I claim that the fluctuations of these things are not very large. Okay, so I'm not going to explain why, but there are classical ways to see this. And just to make sure we don't get confused by these fluctuations, I'm going to take the expectation. Okay, so now it's just a number. And my first question is, can we understand this number? And if beta is very large, this is essentially the same question as asking whether we can understand the value of the maximum of this function. And I want to understand this in the limit of large n. Yeah, I realize that I don't have time, so I have to fix this because at some point this will be a problem. Let me fix this right now. Okay, good. Yeah, so I'd like to understand what's happening in the limit of large n. And yes, and perhaps I should say it's not difficult to understand that this will be of constant order. You can find constant, one strictly positive, one finite, such that you can show this is between these two constants. This is not too hard, but I really would like to identify the exact limit of this function. And the reason is that this is, again, think of this as being a Laplace transform of the thing you care about. If you understand this well, then this will unroll a lot of good properties about the Gibbs measure and other aspects. Okay, so I promise that this is more interesting than maybe it looks at first sight, because as you understand this quantity, you can then progress a lot on your understanding of other aspects of the geometry of the function. And well, perhaps I can spend a couple of minutes to say a little bit of fun stories about this question. So at first, Sherrington and Kirkpatrick, who introduced the model, they had this paper called an exactly solvable model of something. I forgot the exact title. Anyway, they were advertising that they were solving the model, and they were using this language kind of in the way I'm going to use it as well, meaning they can compute the free energy. And so they were doing some calculations in the way physicists sometimes do, not always perfectly rigorous. And then they would find an answer to this question about the free energy. And then they would say, yeah, this is exactly solvable. We managed to compute. But then in some small remark near the end of the paper, they mention in passing that their answer cannot be correct because if you compute some entropy thing, which, okay, this is a discrete model, so in this case, the entropy should be non-negative, then, okay, they find minus 0 something. So something is wrong, but, okay, it's kind of exactly solvable. Anyway, this intrigued the physicists a lot, and in the late 70s, Giorgio Parisi proposed, by doing more sophisticated non-rigorous arguments, Giorgio Parisi proposed a possible answer to this question, which seemed to have less of the disadvantages of the previous possibility. And I'm not going to write it immediately because it's kind of complicated, but I'm going to give you a little bit of a flavor of the formula. So maybe I should write first, this is Parisi. I think the first contribution is in the very late 70s, but then many works in the 80s on this thing, in the physics community. Yeah, and the way it looks like is that it says, Parisi tells you that this should be, this limit should be represented as an infimum over the space of probability measures of some functional, which is complicated and I'm not going to write down, but hopefully I'm going to give you a flavor of what that is as we proceed. Maybe near the end of the lectures we'll have a better view. And I want to just display this because I want to try to give you a sense of why physicists found that surprising at the beginning. So, okay, so first perhaps I should say that the sort of formal calculations that Parisi did to guess this formula were really, how to say, sometimes physicists, they don't always do rigorous arguments, but sometimes they are not, every epsilon and delta is not there, but you see what they mean. This was not exactly in this category, okay? This was more in the kind of very creative sort of solution. And so that was part of it. But also, I think part of the reason they found that very surprising is that, okay, you may know this or not, but the quantity that I wrote on top, even without the expectation, and for each finite n, this is not in the limit, whatever, for each finite n, you can write it as a supremum over probability measures. It's really, when I talked informally, I described the sort of balance between entropy and energy. And you can really make this precise. You can say, for each finite n, this is really a supremum over probability measures of some energy term minus some entropy term. You can really just write it down. And so I think if, and physicists understand this very well, and also if you think about large deviations, it feels quite intuitive. And so I think physicists would have been perfectly prepared to believe a formula that looks the same in the limit. If it had been supremum over probability measures of something, people would have thought, okay, he did some weird calculations, but he kind of figured out how these kind of energy and entropy terms behave as we pass to the limit. Okay, and that's the intuition, and we kind of understand it. And so in particular, I think people suspected that there were too many wild moves, and so there had been a sign mistake somewhere, and this could not possibly make sense. Not every physicist thought that, but at least that was the part of the reason they thought this was confusing. And also at the beginning, there was not a lot of insight into this formula. There was a good guess, and people could check that this entropy that was negative in the first solution was no longer negative in this solution. So at least one sanity check was being okay. But progressively in the 80s, Parisi and other people worked a lot on this and started to understand lots of aspects of this thing and of what it meant in terms of the Gibbs measure and in terms of what the system is doing, etc. And so they became convinced that it looked correct, or at least it was really describing a lot of good aspects of what the correct solution would be. Okay. So yeah, again, I'm not giving a full picture of that, but and for mathematicians, it was fully settled some years later by Francesco Guerra and Michel Talagrand in 2006, I think, who gave a proof of this formula. Guerra proved one bound, and Talagrand proved the converse bound. Okay. And and I'm hiding also contributions of several other mathematicians like Eisenman, Arguin, Bouvier, Bolthausen, Snitman. I don't know. I'm forgetting many names, but several people worked hard on this. And shortly, well, I don't know if shortly, but anyway, a bit afterwards, Dmitry Panchenko gave a new proof of this formula, which is also more robust to, like, it also allows him to cover more models, and is also more insightful in certain ways. Like the way the proof of Panchenko works really understands structural properties of the Gibbs measure better than what the previous approach was doing. So it's very nice. Yeah, perhaps, I'm not sure if I like to do this very much, but just to mention, Parisi got the Nobel Prize in Physics, in part in relation with this, and Talagrand, you may have heard, has gotten the Abel Prize, in part in relation with this. Okay. okay, so this is a mathematical theorem. So you may ask, why am I talking about this? You know, it's already solved quite a while ago now. And the reason I talk about this is that, I don't know, 5 or 6 years ago, I got interested in, I wanted to study a variation of a model like this, which looks like this. It looks like a modest modification of the question, but to this day, I think there are still some puzzles around it. And maybe I'm going to do a drawing first to explain how the system looks like. So I was reading some physics works on that I was trying to discuss aspects of these artificial neural networks thing, which, okay, look interesting. And they were focusing on a version where, so here I'm drawing the units that before they were all indistinguishable, indexed between 1 and n. And now the new aspect is that they're organized over these 2 layers. Okay, there's a bunch of guys in this layer, a bunch of guys in this layer. And they only interact across the layers, but not within the layer. So if I want to make it more precise, I could say that now a configuration sigma is going to be a pair of guys, so sigma 1, sigma 2, a pair of vectors. And okay, in my head, I don't think that they necessarily have the same length, but just for, you know, just to not bother too much with notation, I'm going to put them of the same length in my definition. Okay, so sigma 1 is, this is sigma 1, 1, sigma 1, 2, sigma 1, 3, etc. This is sigma 2, 1, sigma 2, 2, etc. And so instead of this Hn of sigma like this, where this it was sum over all I and j, I'm going to maybe call it with the bip on top for bipartite, because there's this bipartite structure in the graph. Whoops. So a very modest modification, as far as I can tell. So now I'm just going to write sigma 1, comma I, sigma 2, comma j. Okay, only interactions across the types, but not between types. Make sense? And maybe, so I've put them of the same length. So now you can see that there is a symmetry, and I don't want to exploit the symmetry. So if you're really bothered by the symmetry, you can say, you can add a little bit of, I don't know, some twist so that there is a bias in one coordinate. But just forget about this, okay? Let's say this is a definition. Okay, but don't think that there is a symmetry in the model between the coordinates with the 1 and coordinates with the 2. Okay, let's say that they have a different length or something. Okay, so I put the definition over there, but okay, definition is there. And now, okay, so physicists were studying this model because it has connections with these artificial neural networks that perhaps are no longer very much en vogue these days, but classical models that maybe some of you have heard of, like, yes?
So it should be inner product between sigma 1i and sigma 2.
This is really a number. So sigma 1i is just a number.
But we are vector?
Yeah, so by this I mean, yes, thanks for the question. So I mean, maybe sigma 1 is sigma 1, 1, sigma 1, 2, sigma 1n in Rn. And you know, this is going to be a +1 or a -1 if you like, and it's going to be sigma 1, 1, sigma 1, 2, etc. Does that make sense?
Sigma 1, 2 represents the first layer.
Yeah, that's right. So this is the first layer up to sigma 1n, and
So it's like you have matrices of +1 and -1, no? So it's -1 over your real value.
say again, maybe.
So here sigma is like you have -1 then times -1 +1 then, no?
Ah, yeah, you mean maybe I should have written. You mean I should have written like this?
Kind of.
Yeah, that's right. Yeah, okay. Yeah, that's true. Yeah, so I should have. Yeah. Yeah, so, okay. For stupid reasons I'm not going to explain, I like to, okay, anyway, I have this bias to do this. But, maybe that's better. The thing is that, in principle, you could define this function everywhere, and then you just decide you know, when you compute this, you restrict to sigma in +1 -1. So, okay, anyway. It's just a detail, but it makes things clearer if I say it up like this. Other questions, or does that make sense what I'm saying and so forth? Okay, so the keywords for these artificial neural networks things are the perceptron model, the Hopfield model, and I think some of the works that really got me excited in particular were works of Rémi Monlasson and Jérôme Toubiana on models called restricted Boltzmann machines, which were popular up until, I don't know, 12 years ago or something. Now they are perhaps no longer so much in fashion, but anyway, I found them, anyway. So these physicists, they have lots of interesting predictions on what these models are doing, and I thought it would be interesting to try to do some math about it. And you know, as I told you, I think that the first step towards understanding any model like this is to compute the free energy. So I could not immediately spot where what was the reference for finding the free energy for this model, but I thought surely it's kind of, you know, in the convex envelope of the things we already know, or something like this. So maybe by massaging a little bit what the mathematicians have done for this model, I would find my answer. Do you have a question? Or?
So this your first example seems like a generalization of the Fourier model for this with this WIG, right?
Yes.
And for the second example, you can just extend it for the bipartite Fourier model, right?
Exactly. Yeah.
And from there, do you have I mean, is there some explanation for the limiting thing, limiting object?
You mean in terms of the link with the Curie-Weiss model?
Yeah.
Not that I know of. Okay. Yeah, it's really, I don't know, there's something, yeah, perhaps I should have said a bit more about, like, for me, this is really fascinating because, well, okay, I'm interested in this question, but also I find it, from a mathematical perspective, I find it very interesting because, I mean, I don't know, maybe it's the first time you see it, it looks complicated, I put exponentials, sums, logs, I don't know. But in truth, it's a very simple question in my opinion. You know, I wrote down some, you know, it's like a quadratic with random coefficients. And I'm saying, you know, what's the behavior of the maximum of this function over the hypercube? I mean, okay, it's not super simple, but it's not crazy question, right? And the answer to this question turns out to be extremely sophisticated. You know, like I didn't even dare to write it down. You know, it's an optimization of probability measures. We don't even know why it's an infimum. The limit does not look like what it is before. Like for me, this is really, there's some mathematical thing that is happening that is very intriguing. And yeah, I think I'm curious to understand this aspect. And in particular, for Curie-Weiss, I don't know, things feel simpler to me, and I feel I understand. When I try to calculate the free energy, I feel I have some intuition for why the answer is the way it is. Here, okay, I mean, now, you know, after many years, you get used to things, so you call it intuition. So now I find it kind of intuitive in some sense. But yeah, still I find that there is a mystery in a way in this aspect. All right, so anyway, so my first, I thought my first homework when studying this was to try to adapt the proof approach and figure out the free energy for the systems. And well, 5 years later, I'm still wondering what is the limit free energy of these systems. So yes, so at breakfast, we had this conversation with Michal that it's nice to emphasize things that we don't understand also during talks. So this is one question I would really like to solve, and that I don't know how to solve, is what is the limit free energy of this model? You know, you ask the same question as here, but you put BIP here. What is the answer? I don't know the answer to this question. Okay, so it's been 5 years, and so we haven't done nothing in the meantime, and I'm going to tell you some of the journey through which we went and the sort of things we have done to try to understand this. But to this day, it's still an open question. What is the true answer to what is the limit. In fact, even the existence of the limit is not threatened. Like, we don't know that the limit exists if you put BIP inside the here.
Can you prove it's bounded?
Yes, yeah. So we know it's bounded between two constants. This is not too difficult, but that's I mean, we know other things, but I'm going to tell you what we know. But that's where we are. I had an interesting question, which I basically boiled down to, so what's the difference between these two things? Why is this difficult and this one is less difficult? And I think the way I presented to you these functions is I gave you a formula for them. But if you think about it, this we said is Gaussian. And so I could just have told you this is a centered Gaussian field. And I just give you the covariance of this field. I don't need to give you a formula. At least this is another way to think about a Gaussian function. And I think this is actually more useful in many ways for thinking about this specific problem. So let's do this calculation real quick for these two cases about the covariance of this random field. Maybe if I write here, you will not see much. So just let's go back a little bit to the SK model first. Maybe I'm going to write SK to make it very clear. If I take two configurations and I compute the covariance between Hn of sigma and Hn of tau. Okay, so it's very easy to write down. It's just independent Gaussian. So you imagine, I'm not going to write the calculation, but imagine you write sum of Wij sigma I sigma j, and then sum of I prime j prime, tau I prime, tau j prime. The covariance will be 0 unless ij is the same as I prime j prime. And so you'll have sum of sigma I, sigma j, tau j. And so you see a sum of sigma I, tau I that wants to go together, and the sum of sigma j, tau j want to go together. In other words, what you'll get is the scalar product between sigma and tau squared. Okay, and then there are some normalizations, which, please believe me, it's like this. Okay, so this is what you get. And what really I want to emphasize, so if you want, alternatively to the way I described to you the problem, I could have told you, look, a mean field system is going to be described by a standard Gaussian field whose covariance I can write down in terms of the scalar product between the two configurations. Okay, by mean field, I take it as, okay, it's just a function of the scalar product. So you have this symmetry kind of built in. And then really the only thing that you need to specify then is what is the function of which we are the scalar product. And here it's the square function. Okay, and this is for SK. And if I do it for the bipartite case, whoops, this is expectation. Well, the calculation is very much the same, it's just you have to pay attention to the indices, but it's not crucially different, so I'm not going to do it again step by step. But what you will find instead is that you'll have the scalar product between the two, sigma 1 and tau 1, and then multiplied by the scalar product between sigma 2 and tau 2. Okay, instead of this square, you have it being split between these two things. And really, technically, the difference is that here the key function is the function that takes two arguments and gives you the product, while here the key function is you take a number and you give you the square. And this function is convex, and this function is not convex. Okay, and this is what really separates the world of things we really understand well, the world of things where the function is convex, from the world of things we don't understand as well, which is the world where this function is not convex. And okay, there's some technical. Okay, anyway, so this is the key thing. And you see, when I present it like this, you have more freedom to, like for instance, if I put a power of 4 or a power of 5 here, you can still show that there exists a Gaussian field with this covariance, and you can still explore the spin glass question. And then it will no longer look as much like a sort of random matrix thing. And so that's why maybe when I write this, you think, oh, maybe we can use random matrices. And I'm not saying it's not a good idea, but it's just that in general, I would like to find techniques that work even if I replace the two by something else. Okay, just some arbitrary function, let's say, of the scalar products. And yeah, there is this kind of dichotomy between functions that are convex and functions that are not convex, which I would like to explore. And yeah, so I told you that in the 5 years we have not done absolutely nothing, even though we cannot answer this question. So let me say a few things we've managed to do. So yeah, the first thing is that it's not even clear what it is that you're supposed to try to show. So the first question you can ask is, can I just guess what is the correct answer if here I put BIP for the bipartite? Oh yeah, maybe I should say also, again, I described the bipartite thing, but really it's just an example among whatever you can imagine with a finite number of types of spins, okay? So if you understand, like, the sort of things I'm going to discuss, they work just the same if you put, I don't know, a finite number of layers, for instance, or whatever. As long as there's a finite number of types of guys in your graph, let's say, things will be the same as this one. Okay. And if it so happens that what you write here is a convex function of the scalar products, then in fact we understand a lot of things. We can write the Parisi formula, etc. Yeah, so the question, the first question, perhaps you try to confront, or I mean, I don't know if it's the first, but is if I write BIP, what is a good candidate for being the limit? At least personally, I find it an interesting place to start. And well, you can look at the formula for the SK model and try to imagine how it could possibly generalize, and you can write a number of candidates. And one of the things I did at the beginning is write these candidates, and then I could show that each of them is actually incorrect. Okay, so maybe I was not imaginative enough, and maybe there's a better way to find how it extends, but at least at the moment, that doesn't seem to be a good way to generalize this formula. And so it felt to me like there was a need for thinking about it in a somewhat different way. And that's why I started to think about these partial differential equations. And so now the thing I'm going to try to argue about during these lectures is that you can think about this object, and maybe you will have more arguments than just beta, but this has a function of beta and maybe of other things. We are going to try to say that it's trying to solve a partial differential equation as we send n to infinity. And so then what happens in the limit is not some explicit formula necessarily, but just that in the limit you do solve the equation. And so this gives you a description which, I prefer variational formulas. I like this. It's kind of perhaps more convenient to study, but sometimes you do what is true. I mean, there's no. So this will be, at least this is one possible way to conjecture a limit, is to just try to describe it using a different language, using partial differential equations. And perhaps it's also, at first I thought it would be a proof technique, and then a posteriori we would manage to write down the PD in variational terms, but this doesn't seem to be valid. So now it's also a part of the conjecture that the limit is described by the PD. And yeah, okay, so maybe I don't say more than this. So let's say for bipartite model, conjecture, let's say. And it's really a conjecture. I mean, okay, I don't know what is qualifying as a conjecture, but I really don't know if it's true. It's a plausible candidate, but it may be true, it may be not true, I don't know. Conjecture for the limit. In terms of some partial differential equation. And so in particular, for this specific thing, the answer will be solve this partial differential equation, compute the solution at this specific point, and this is the limit. That will be the phrasing of the statement. And we proved one bound is proved. And I'm going to get it wrong, I guess, but I think it's this bound. I'm going to stare at Victor to confirm. It's okay. You tell me if I get the inequality correct. Okay. Anyway. So that's one thing we did. And then more recently, with Hongbin Chen, okay, so maybe I should say, physicists, when you talk about them, okay, it depends on who you talk, but some are not even aware that there's a difficulty. And that's a little bit confusing because, from a mathematical perspective, I tell you, I don't know what is the limit. But in general, the way they will discuss what this is doing is that, so you have a functional here, maybe I'll give it a name. Let's say it's P of mu. And in these cases, my understanding of what they say, at least, is that they're going to tell you, they're not going to tell you you should minimize. They're just going to tell you, oh, you should look at the critical point of this functional. And then the free energy will be that functional calculated at the critical point of this functional. Okay, so this is my kind of translation of what they do, but I think it's a fair representation. Okay, and they don't specify exactly how you pick the critical point. And that's for a mathematician, this is the mystery part, because it doesn't give you a complete description of the object. You're told to pick a critical point. By critical point, I mean a point, a mu, such that, think of this as being a finite dimensional object. You look for an argument such that the gradient of the functional at that point is 0. Okay, so maybe it's a maximizer, maybe it's a minimizer, maybe it's some saddle point, whatever, you don't know. But it's a place where maybe it's nothing. But anyway, this is a critical point. And once you find, you find a critical point and you pick the correct one in some way, which I don't know. And then you calculate this functional at that critical point, and this gives you the correct value. And in fact, at the beginning, I even thought that this maybe was not correct, to be honest. And so, I was just leaving it at that. But then, with Hongbin Chen, we didn't manage to prove that this is true. So the statement we showed is that if we assume that the limit exists, then we can show that that thing is true for some specific functional which we identify. Okay, so let's say with Hongbin Chen, we showed that, let's say, a critical point representation. Okay, I'm not going to write it on the board, but I hope you understand what a critical point representation. Okay, this thing of, there exists a critical point such that this is a critical point, assuming the limit exists. And so this is a bit unsatisfactory because it doesn't give you a full description of the object. And also, perhaps it's a little bit, perhaps one frustrating aspect of this is also that we have to assume that the limit exists, which we don't know how to show. But okay, perhaps this is a bit related to the fact we don't know how to fully identify the limit. So personally, I put more of my effort towards trying to narrow down what should be the correct limit. And I think if we really understand what should be the correct limit, the existence of the limit would kind of follow as a sort of byproduct because basically if we know how to identify the limit, then in particular we'll manage to show convergence or something like this. But anyway, so just to say that this is conditional on the existence of the limit, but in this work with Hongbin, we also have results where things are not conditional. We can say up to extraction of a subsequence, we understand the structure of the Gibbs measure like so and so in terms of this critical point, okay, which you choose in a way which I don't specify. And so we didn't show that, but we expect that typically there will be a finite number of critical points. And for small values of beta, for instance, there will be a unique critical point in general, but then at some point there will be several, and indeed you have to choose, and then I let you do the choosing. Okay? I don't know how to do it. Yes, so that's all for this part. Are there questions on this, or?
Are this problem like calculus of that mu for calculus of variation? There are problems that functional that you write down are functional that are really new, or like something that has been studied like in other branch of mathematics,
So the
to start with.
if you write this formula in some way, let's say, I don't know, at least there are ways to write this formula for the Parisi functional so that basically you write the correct functional already. And so it's an optimization over a space of priority measures. And yeah, it feels more like it wants to do transportation sort of derivatives. Anyway, so there are, even for the PDE part, you have to phrase PDEs in these infinite dimensional spaces, and there were some works, but we had to do a lot of stuff on our own as well.
It's also challenging from the point of view of calculus.
Yeah. I think there are some. I mean, I think there are questions that I think physicists are interested, for instance, in. They do run numerics on these sort of things, and they do want to calculate the. Like, even though I don't know how they choose the critical point, they do and find it. So, they are good, Then when they find several, they have their physical flair to tell them that this one is the correct one and so on. And, so anyway, they have lots of tricks to kind of guess what is the correct critical point, and they do numerics. And even understanding the behavior of the numerics, I think, is a very interesting calculus of variation sort of question where, anyway, I'm not going to explain how they do their numerics, but they see interesting phenomena, which I think, anyway. So I think there are lots of pure math questions related to also just doing numerics on this functional, for instance. Yeah, and I think using some of the results I didn't show, but I didn't write down about the description of the GIST measure, you can already start to, I told you that we were motivated by questions of physicists doing lots of interesting observations on these models. And hopefully, I think with these, we haven't tried yet, but it's plausible to me that you can already start to unroll some of these things, because in the end, physicists were not using much more than the fact that it is a critical point of this functional and blah, blah, blah. So I find it plausible that you can still reap interesting fruits from this result, even though it's not as complete as I would like to, but okay. Yes, so this is it for my spin glass presentation, and now I'm going to briefly mention the two other models I want to discuss during these lectures. So the first one is one you mentioned earlier. I don't know your first name, but you. The Curie-Weiss model. So this is end of spin glass part, and I told you I was going to also think about two other classes of models, and maybe I'm going to erase some board. To explain this. And the first class is going to be, so we're going to call them, or they are called the Curie-Weiss model. The Curie-Weiss model is the model you get if instead of doing this, the way we defined it, you choose the Wij's to be constant equal to 1, let's say. Okay? So this is, so it's not disordered, there's no glassiness, there's no frustration in the model, but it's still a good playing ground for trying to understand what techniques we can develop. So it's Wij equal to 1. There are many ways to understand the free energy of this model in this case. In particular, you can use results from large deviations, which I'm going to recall briefly in the next lecture probably. So you can compute the free energy without thinking ever about partial differential equations. But we are also going to, so first I'm going to explain how you do this. And so we'll know what is the answer then. And then we're going to try to recover this result using partial differential equations. And try to make sure that it works well. Also for variations on the Curie-Weiss model, which I'm going to discuss next. And we'll try to make sure that our partial differential equation techniques really work well on this very simple model. And once we have this, we're going to move to yet another class of models, which comes from statistical inference. And let me see how much time I have. 10 minutes. Oh, maybe I can still say some words. So first, maybe let me say why I would like to talk about these models. Well, I think they are interesting on their own, and from a mathematical perspective, the reason I'm really eager to discuss them is that, at least for the specific question I'm going to ask and the specific models I'm going to focus on, they look and feel a bit the same as spin glasses, only easier. And this is nice, because we're trying to develop our toolbox. And as you have seen on this part of the board, we're still kind of struggling with spin glasses. We still don't have full results. So maybe it's good if we make sure that we, at least we can really cover everything that needs to be covered on simpler cases. And so I'm going to discuss that also for that purpose. In particular, the tools we're going to develop for the very easy models, they're going to just apply straight away on these ones as well. So it's interesting to see them working at least to the full extent, not with this kind of complicated, if you assume the limit exists, then maybe something good happens sort of move. And there are different ways to motivate the sort of problems I want to describe. The one classical one is to refer to a problem of community detection. So imagine that you are like, I don't know, Facebook, and maybe it's the US political landscape, which is very polarized into two communities, and you don't know which person belongs to which community in advance, but you can see who is friends with whom. So just to bring this back to mathematics, you're going to build a random graph, and inside this random graph, there will be each node will be assigned a community. Let's say there are two communities, and maybe, I don't know, the first, you have n guys which are in community +1, and you have n other guys which are in community -1. And then between each pair of individuals, you're going to draw a link with a certain probability, and you will put a higher probability if the two guys are in the same community, and the lower community, they are not in the same community. And you do that, so you create a random graph, and then you give the observer only the random graph, but not the community structure. And the nodes are not organized, so you just give them the graph. And the question is, can the observer recover information about the communities from the observation of the graph? So from a mathematical perspective, there are really two different regimes that you need to distinguish. There's one regime in which you set the problem so that, so we're interested in large systems, okay? And you can set it up so that as you make the system become very large, the average degree of a node remains bounded, or you can set it up so that it diverges when n goes to infinity. And this will lead to very different behaviors. When the average degree remains bounded, this is the sparse case, also related to the question you had in the. Then the problem will be rather difficult, and I told you statistical inference is easier than spin glasses, but then if you're in this sparse regime, it becomes harder again, and so then we have results which have a feeling a bit like this one. Like it's kind of complicated. We have a conjecture, we have lower bound. We have this critical point thing. Anyway, like things become complicated again. But if you're in this other regime, like in this dense regime, where the average degree of a node diverges as you send the size of the graph to infinity, then in fact you have some interesting averaging that is happening at the level of each of the nodes, a bit of like central limit theorem sort of effect. And you can show that the model kind of basically is equivalent to a much simpler model where you just observe something with a Gaussian noise. Like I'm going to write down, maybe I'm not explaining this very well right now, but I'm going to write down the simplified model right away on the board. Okay, so I'm saying that this community detection problem, as long as this degree diverges with the size of the graph, you can reduce it to the problem I'm going to write down on the board now. So suppose you have a bunch of variables, and they are independent and identically distributed. Let's say they are bounded, real-valued random variables. Think of them as being +1 and -1. You know, maybe they are the communities. And okay, I changed notation. I don't call them sigma anymore, but okay, bear with me. I like this notation in this case. And what you're going to observe, let's say I'm going to call it y, is going to be, okay, some coefficient times x bar transpose. Okay, I'm putting star to mean the transpose of x bar plus noise. Okay, this is my good old Wij, a bunch of independent standard Gaussians. And this is just fancy way to mean that for each I and j, you observe, okay, square root of 2t over n times x bar I, x bar j, plus Wij. Okay, this is what I mean by this matrix notation. Yeah. So if you imagine this is +1, -1, the communities, you see you're seeing basically whether or not I and j are in the same community, but with some Gaussian noise. Okay?
Why do you put a time?
Yeah, and it's just a parameter. I could have called it beta, and you would have perhaps been less stressed out. But I fancied to call it t for some reason. Okay, so t is just some fixed parameter. And you know, you can think of it as a signal-to-noise ratio. If t is very small, you basically only see noise. If t is very large, you really see the data very well. Okay, and I'm not explaining why this is related to or has a feeling similar to spin glasses right away, but okay, maybe I can say one word. So the question you're asking is, what can you understand from x bar given this observation? And so it feels like at least one thing you can do is try to write down what is the law of x bar given the observation. And when you do this, because of this Gaussian thing, okay, I'm not going to do the calculation, but you're going to see that, well, we're going to do it later, don't worry. When you do this calculation of what is the law of x bar given the observation, you're going to see showing up some exponential of Wij, x bar I, x bar j, okay, which is basically the function which is there. And for some reason, which I don't explain, I claim that this model is actually simpler than the spin glass case. I don't explain it because I don't have a very short explanation, but it's true. And what else do I want to say? Yeah, so just examples of questions we're going to study. Maybe what you would like to understand is what's the behavior of, you would like to recover information about this guy, about x bar, or about this matrix x bar transpose. So maybe you would like to study x bar transpose minus, let's say, your best guess about, oh no, maybe I should not write like this. Let me write like this. Let me write z. I forgot the square. Like this. Z is y measurable. Okay, so you only observe y. So the best thing you can do is something which is a function of y, or something which is y measurable, or maybe I should write sigma y measurable, I don't know. And you try to do the best you can like this, okay? So yeah, z is the conditional expectation, which I was almost kind of writing, but just to clarify. So yeah, z, the best thing you can do is the conditional expectation of x bar transpose given y. But okay, this is what I think it's the best way to think about this. And so the sort of things we're going to be able to show, well, for instance, we're going to, so maybe, okay, if I want to normalize this, I think I have to divide by n squared. And we're going to be able to identify exactly what is the limit of this object. And in particular, in the case when the expectation of x bar is 0, like if these variables are centered, for instance, if there are, if this is +1, -1, and it's probability 1/2, 1/2, then what we're going to see is that when t is smaller than a strictly positive number, so maybe let me write this. So for instance, we're going to just identify the limit of this in general. Okay, so but in particular, if one of these variables, if these variables are centered, then we can show that there exists a critical signal-to-noise ratio, TC, which is, maybe I'm going to use French notation for this interval, between 0 and +infinity, excluding the endpoints, such that if t is smaller than tc, that guy converges to 0 as n goes to infinity. In other words, basically you have no information about this community structure. And as soon as t is above tc, you can do better. This thing, we're going to see exactly what it converges to, but it converges to something which is strictly positive. Okay, which depends on t, of course. And that's something we're going to first identify it using partial differential equations, and then we're going to see also that we can write it in variational form a posteriori. Okay, but we're going to use the PDE as a proof technique towards identifying this object. Okay, so this is basically the plan of the lectures. We're going to first work our way through this simple model, and I mean, I don't know, maybe you're impatient and you want to talk about the real things, but in my experience, it's really, I learned a ton of things thinking about this. Like, it's not just I use it in the lectures. When I work and try to think about my research problems, I do spend a lot of time thinking about this simple case. And I really think there's a lot of value to thinking about this. So I'm going to also talk to you about this simple model. And then we're going to train our techniques and learn a bunch of things. And then we're going to study this, because I also find it interesting, and we see this PD blah, blah, blah working kind of nicely. And hopefully, I will also say a few words about the spin glass case, which, okay, is more demanding, but that's the plan, if there's a question. Yes, that's true, yeah. So this CT is going to be increasing. That's your question? By increasing, I also mean the French way. You put all the double negative, if you like. But, yeah.
If I understand well, if t is equal to 0, then y is only a noise. So it should be
0?
Shouldn't it be big? Because it should
Oh yeah, you're right. Yeah, sorry. So yeah, I meant, yeah, you're right. I said it the wrong way. Yeah, you're absolutely right. Yeah, I said it the wrong way. Yeah, I guess I should mean, I meant the different, yeah, you're absolutely right. Thanks, thanks a lot. I said it just the opposite way of what is reasonable. This is going to converge to what it converges to when you set z equals 0. So, okay, yeah, sorry about the confusion. So what is it converging to? Maybe it's something like this. Okay, to be verified. But anyway, the thing that you get when you set z equals 0. And then it's going to be strictly below this. And it means you're really doing something interesting. You're really recovering something. And the reason I got confused is that we're going to study some specific object, and we're going to compute its alignment with the true thing. And so in my head, I was thinking, what is the scalar product between our guess and x bar? And this is what I was writing in my head. That's why I got confused. So if in my head, I think there is our guess, there is x bar, and what is the scalar product doing in the limit? And in this regime, it's 0. We are just doing nothing. In this regime, we have positive correlation with the truth. Okay, but yeah, I kind of mixed up. Thanks for the clarification. And then this limit CT In fact, it's decreasing. I said increasing, but yeah. Sorry about the confusion. Thanks a lot for the question. Other questions or other things? Other stupid things I've said?
What happens at TC?
Yeah, it depends then. It will depend on the specific law of x bar 1. So you can have cases where the limit is like here, and you can have also discontinuities there. It just depends. You cannot, you cannot specify at this level of generality. Other questions? Well, if not, then I think that's it for today. See you tomorrow.